Okay, so in the last video you looked at rotations, and here it is typed up. A little neater than it was on GeoGebra with the x prime and the y prime separated there. So there's how to do a rotation about any point in the plane which has coordinates hk by an angle of theta. Okay. Again, I'm not going to do the numerical examples in the video. You can look in the book and they do have numerical examples of these. I can't remember if it's the exact same coordinates. I probably changed the numbers a little bit, but you can see very similar examples to what I have here worked out in the book. Or you just plug the numbers in and crunch it out, plug and chug, right? Now let's look at reflections. We're going to look at reflections. First, it's pretty easy, and you've probably before seen reflections across the x and y axis. You just have to reverse one of the coordinates. We'll think about that, and then we'll start building up off of that. So we have corollaries here, how to do a line, horizontal and vertical lines, and so forth from there. So let's see. Okay, so here is a picture in GeoGebra of a point with coordinates x, y. I can move that point around. And if we replace x with negative x, that just gives us the reflection across the y-axis. So if I want to take a point and reflect it across the y-axis, just replace the x with negative x, or multiply the x-coordinate by negative 1. If we do that to the y-coordinate and go from y to negative y, we get the reflection across the x-axis. Okay. Now I forgot to do a GeoGebra for horizontal and vertical lines. Let's say we have the line like y equals 2, a horizontal line, and I want to reflect across that. What I can do is first translate everything to the x-axis, reflect, and then translate back. Or if I wanted to go across a vertical line, like say x equals 1, I could move everything to the y-axis, translate across, and then translate back. Let's go see what the formula works out to be for that. So that's the corollary here. It's pretty simple to work out. I'll let you look at that on your own. But if you want to translate across a line that's parallel to the x-axis, first shift it to the x-axis by subtracting off the y-coordinate, and then you add it back. You wind up with a 2k in there when you do that, and you change the sign of the y when you did the reflection across the axis. For the vertical lines, you have to subtract off h, and you wind up adding it back and distributing and everything, and it works out to be these formulas. So if you're going to reflect across a horizontal line, y equals k, it winds up the x stays the same, and after you do the translation, the reflection, the translation back, the y-coordinate winds up being either 2k minus y or negative y plus 2k. If you're going across a vertical line, x equals h, the y stays the same, but if you're actually deriving the formula, first you translate everything to the axis, and then you rotate or reflect, and then you translate back. It winds up being negative x plus 2h or 2h minus x for the x-coordinate. Okay? Again, there's some numerical examples you could look at in the book. So pretty simple formulas, really simple for rotating across, reflecting across an axis. And pretty simple too, short little formulas, little linear formulas for reflecting across a parallel line to the axis, a horizontal or vertical line, parallel, perpendicular lines there. If your line is not parallel to one of the two axes, and you have a slanted line with a different slope, so this is we're going to start with one through the origin. This is a line y equals mx. Okay? And we know we can identify that line by its angle of inclination, which I have in the picture here. Okay. So here's the idea. I actually have this one worked out in GeoGebra to derive the formula. So I want to reflect my point xy across that line. The first thing I could do if we go through the origin is rotate everything around the origin. Okay. We had formulas for doing that. And in this picture, I would want to rotate by negative. The angle's alpha here. I would rotate by negative alpha because I want to go in the clockwise direction. So I just take our formula for that. X cosine my angle minus y sine of the angle, x sine of the angle plus y cosine of the angle. Then I can apply the fact that cosine is an even function. Cosine of negative alpha is just cosine of alpha. Do the same thing over here. Sine is an odd function, so I have to pull a negative out. So when the negative comes out, this actually becomes a plus, and then the negative goes in the front here. Then we can reflect across the x-axis. Okay. So we rotated down to here, then we reflected across the x-axis. That changes the signs of the y-coordinates, so that negative becomes a positive, that positive becomes a negative. And then we rotate it back, which gets a little messy. The formula actually turns out to be quite nice. There's some really nice applications of the trig functions here, the trig identities. But if I actually rotate it back by this time alpha, because I'm going in the positive direction, I would take my x-coordinate, which is the x-coordinate of the previous point, which is kind of complicated because it's already been rotated. But it would be that times cosine of alpha minus the y-coordinate times sine of alpha. That would be my new x-coordinate. I can distribute and group things. If I've put the x's together, I get x times cosine alpha out of this first piece. And if we look over here, we have an x with a minus sine alpha. So I get x times cosine squared alpha minus sine squared alpha. This is actually the addition formula for cosine. So alpha plus alpha, I get x times, it's just cosine of 2 alpha. Similar thing happens over here. If we factor the y's out, I get sine alpha cosine alpha. And over here I get the same thing. I get a the minuses cancel, 2 minuses, and I get a cosine alpha and a sine alpha. That's the addition formula for sine, so I get y sine 2 alpha. So the x-coordinate takes quite a bit of work to get to it here in the derivation, but it turns out if I want to wind up with this blue point that's reflected across the line, if I first rotate, reflect, rotate back to get it, it winds up the x-coordinate is just x cosine 2 alpha plus y sine 2 alpha, where alpha is the angle of inclination. The y-coordinate, you get those formulas again. It looks a little bit different. The formula was a little bit different. Sines and cosines are crossed and some things. But you wind up again getting the double angle formulas. And the y-coordinate comes out to be x sine 2 alpha minus y cosine 2 alpha. So in blue there we have the formulas for that point. Okay. If we want to rotate, we don't have to go through all of the composition here. We have the final formula. If I have y equals mx, and I know the angle of inclination, which we can find is the arctangent of m, if m is the slope, we had the relationship between those things. So if we want to reflect across that line, there's the formulas in blue. Okay. The last thing we want to do is reflect across the general line y equals mx plus b, and we're just going to have to shift to the origin, rotate, reflect, and shift everything back. So I've done the hard part of the derivation already here, but so we have a line this time y equals mx plus b, and I can change those things if I want to, change the slope or the y-intercept. That vector's used in a minute. So let's say we wanted to reflect A across this line. Well, the first thing I could do, I could throw it onto the previous derivation if I translate by the vector, the one going down, 0 to b. I translate everything down by b. Then now our line goes through the origin, and we can reflect the point across that using the previous formula. So our new point is x, y minus b, because we subtracted b from everything. And then we would reflect, which would be the previous formula, which was x cosine 2 alpha plus the y-coordinate of that point, which is y minus b times sine of 2 alpha, and then x sine 2 alpha minus the y-coordinate of that point, cosine of 2 alpha. That was the very previous theorem. And then translate back just by adding b to the y-coordinate. So these things get a little messy and overlapping here. But there's the final result after we do it. If I hide some of these other things, let's see, translate back, I want to see that, get rid of that, get rid of that. There's my final result, the reflection across that line. The x-coordinate looks very similar to reflecting across a line through the origin, but it has the y minus b. X cosine 2 alpha plus y minus b sine 2 alpha, because we had to translate everything down to the origin first. And then translate it back, but that didn't move the x-coordinate. X sine 2 alpha minus y minus b cosine 2 alpha plus b. Okay. So again, if you look at that formula, it looks a lot like the rotation about a line through the origin. The difference is you have the y minus b's because we had to first shift everything to the origin and then do the transformation. And then when we shifted back, it added an additional plus b just to the y-coordinate. This transformation, we're just translating by a vector that's changing in the y direction when we do that. Okay. So there's the formula for, the most general formula for a reflection across any line, y equals mx plus b. You have to know the angle of inclination to do it, and you have to use our previous analytic geometry to find that. So that's reflections.